Hi, I'm Sarah Helms, and this is for the Case Connections 2 assignment. So let's see here. Find it. Okay. So I am based out of Lexington, Virginia here, and I'm going to respond to Case Connections for Unit 2. I'll be addressing two cases. Case 2, dealing with regulation of glucose uptake in a brain tumor, and case 4, which is about a 2-month-old presenting with hepatomegaly, not sure how to pronounce it, but that's what it is, and irregularities in both maintaining blood glucose levels and in responding to epinephrine. So I'll get started with case 2, the brain tumor. Case 2, like I said, shows a brain tumor with significant necrosis, and we're asked to look into aspects of glucose regulation that might be involved with the tumor. So let's keep in mind that necrosis, just as defined by Google, is the death of most or all of the cells in an organ or tissue due to disease, injury, or failure of the blood supply. So in this tumor, we are looking at some cell death. However, after administration of fluorescently labeled D-glucose, that labeled glucose shows up in a PET scan located in the area of the tumor, and significantly not nearly as heavily localized in the general brain tissue. So it would seem that the tumor got far more than its fair share of the glucose. So we need to consider why glucose uptake would differ in the tumor. To do this, it's helpful to first lay some groundwork and think through glucose regulation under what would be non-cancer circumstances in these mainstay tissues, liver, skeletal muscle, brain, and adipose tissue. So because of the nature of this case, I'm going to go into a little more detail on the fed state, because after the glucose is administered, then we're thinking about glucose uptake in a fed state. So in the fed state, all of these tissues are using glucose as their main energy source, and insulin levels are high, insulin being released from the beta islet cells of the pancreas. And the liver has a GLUT2 transporter, which is insulin independent. So interacting with that transporter is the glucokinase enzyme, which is always active in the liver, but its isoenzyme hexokinase is activated by the presence of insulin. It's all to say there's a lot going on in the fed state liver: glycolysis, glycogen synthesis, aspects of the urea cycle, pentose phosphate pathway, tricarboxylic acid cycle, cholesterol and fatty acid synthesis. In contrast, in terms of their GLUT transporters, that's GLUT, like GLUT transporters, skeletal muscle and adipose tissue have transporters that are insulin dependent. So they exist intracellularly and move to the plasma membrane to bring glucose into the cell in the presence of insulin. The brain, however, has GLUT1 and GLUT3 transporters that are also insulin independent, like in the liver. And in the fasted state, some of these tissues that we're talking about, like the liver and the skeletal muscle, will switch. They'll begin to use free fatty acids as their main source of energy, using beta oxidation of fatty acids. But the brain always has a preference for glucose, needs glucose for at least 80% of its energy, even in a fasted state. So switching back to the fed state, the brain, which we're thinking about with these images, is using glucose for glycolysis with its GLUT1 and GLUT3 transporters, while the skeletal muscle GLUT4 transporters uptake glucose for glycolysis alongside glycogen synthesis, protein synthesis, and the tricarboxylic acid cycle. The brain, of course, has a few other things to do with the glucose, like maybe ketone bodies. Well, not ketone bodies, sorry, but there would be like nucleotide synthesis. Adipose tissue also engages in glycolysis and is storing excess glucose via fatty acid synthesis. So that's all to say, concluding this background, we can just know that in the fasted state, while there obviously isn't free glucose uptake, or insulin stimulating those insulin-dependent transporters. For the brain, glucose is still its main fuel, and in the fasted state, like I said, it would be relying on hepatic glycogenolysis and gluconeogenesis. So back to our case, when this patient is then administered fluorescent glucose, we see that the cancer cells must have some advantage in glucose uptake because they hog all that fluorescent glucose. So what could the mechanism be? Is there an enzyme in a cancer cell's glycolytic pathway that has a lower Km, thus a higher affinity, and is more readily saturated with the glucose? Or would it be something with a transporter specific to the cancer cell? We got lucky. I did find a great 2016 paper from the American Journal of Cancer Research that beautifully elucidates this case. The paper is titled Glucose Transport, Meeting the Metabolic Demands of Cancer and Applications in Glioblastoma Treatment. And I'll focus on that first part, the meeting the metabolic demands of cancer. So it is known in general that expression of GLUT transporters is under transcriptional control and responsive to the metabolic demands of a tissue. And cancer cells use glycolysis, not oxidative phosphorylation like your average fed state cell, as their main source of energy, even though that's not as efficient in terms of quantity of production of ATP. Oxidative phosphorylation creates more ATPs. But this is called the Warburg effect. It was defined by its namesake, I think Otto Warburg, in 1927. And the paper specifically says, to quote, "In order to engage in the Warburg effect, the cancer cells use much more glucose than a normal cell, so it follows that the ability for such cells to bring glucose into their cytoplasm needs to be increased." And that's what we see here in this image. And this is accomplished by upregulation of these GLUT transporters. In glio or glioblastomas, a type of brain cancer, perhaps what we see in case 2, according to this journal, show upregulation of the GLUT1 and GLUT3 transporters, kind of confirming what we're seeing. To put that in layman's terms, the cancer cells, because of upregulation of the GLUT1 and GLUT3 transporters, have more feet on the ground, more transporters in the membrane. So they are able to create the effect of this heightened state of glucose uptake, and we see the fluorescent glucose there in the tumor. So, going to move on to case 4. Case 4 tells us that there's a 2-month-old that was healthy, but mom came in because that 2-month-old is now jittery after breastfeeding. Even though the feeding has not changed substance-wise, all she's had since birth is breast milk. Sleep could be a factor. The baby has just now been sleeping more than 2 hours between breastfeeding, or time could be a factor. And you can think it makes sense that we are seeing low blood glucose, and that the baby maybe isn't able to maintain blood glucose. That could be a source of the jitters. That was a test result. There's low blood glucose. And then there are 2 more things to think about in the case. An administration of epinephrine does not increase blood glucose, only blood lactate, and there's hepatomegaly or an enlarged liver. So we're given 4 options to think through. Could it be hereditary fructose intolerance, galactosemia, glycogen storage disease, or glucose 6-phosphate dehydrogenase deficiency? So a few mouthfuls to work through. I'm going to start with this idea of maybe it being a hereditary fructose intolerance. That would mean a deficiency in enzyme aldolase B. Fructose, which doesn't have to but could and does often come from the metabolism of sucrose by the enzyme sucrase, which is a disaccharide There's glucose and fructose residues. Glucose can, of course, just enter glycolysis. Fructose has to have this special pathway. So fructose is first phosphorylated by fructokinase in fructose metabolism. And the resulting fructose 1-phosphate is broken down to DHAP, dihydroxyacetone phosphate, and glyceraldehyde 3-phosphate. DHAP can, of course, isomerize to glyceraldehyde 3-phosphate, so fructose achieves a state where it can enter back into the glycolytic pathway. But if there's a problem with aldolase B, we get a backup of all that fructose 1-phosphate product. Because that is ultimately a lack of free phosphate, hereditary fructose intolerance would eventually inhibit glycogenolysis and gluconeogenesis. But we can rule this out because the baby has not ingested any fructose. Lactose from milk breaks down to a galactose residue and a glucose residue. So another thing we're thinking about is if it could be a potential deficiency in glucose 6-phosphate dehydrogenase. That means we need to talk about the pentose phosphate pathway, where glucose 6-phosphate dehydrogenase is the key regulatory enzyme. So if there was a deficiency in that regulatory enzyme, then we wouldn't have as many products from the pentose phosphate pathway. We would have decreased NADPH and decreased ribose 5-phosphate production, and we would see debilitating consequences for fatty acid synthesis, which relies on NADPH, and for nucleotide synthesis, which relies on the ribose 5-phosphate. NADPH is also critical, especially in red blood cells, which lacking mitochondria can't use, potentially use the citrate lyase related pathway to create NADPH because that's taking place via the tricarboxylic acid cycle in the mitochondria. So red blood cells would need NADPH for reduction of glutathione to remove harmful oxidants. And so we would see erythrocyte red blood cell hemolysis from the accumulation of those oxidants given a glucose 6-phosphate dehydrogenase deficiency. But that's not the case here. So could it then be galactosemia, which is a deficiency of galactose 1-phosphate uridyl transferase, or GALT? While GALT deficiency would inhibit glycogen metabolism, so there's, I feel like you're getting warmer with the low blood glucose. A GALT deficiency blocks galactose metabolism, and this is not an issue for the baby. It's been digesting the galactose just fine, or metabolizing it just fine. So that leaves us with the glycogen storage disease. And this is probably the case. This is not in my script at the moment, but another thing that leads us to the glycogen storage disease is that there was not any responsiveness to the epinephrine. Let's see. An administration of epinephrine does not increase blood glucose. Usually, epinephrine increases blood glucose if you think about when you're exercising, when you're scared and you need to move, and your muscles are needing ATP to create that movement, then epinephrine would be generating glycogenolysis so that you could have glucose available to create ATP to fuel that movement within your muscles. That doesn't take place here, though. There was no response to the epinephrine. And specifically in our textbook, there's a glycogen storage disease cited called Forbes or Corey disease. It's a deficiency of the liver and muscle debranching enzyme that would release glucose following the activity of glycogen phosphorylase. So we're breaking down the glycogen. With these enzymes deficient, we see fasting hypoglycemia because you can't get glycogen, or you can't get glucose into the blood when it's not coming from the diet because it's not coming from your glycogen, your glucose stores. And you also, another symptom is hepatomegaly in infancy. And from something that I looked up on the NIH website, this affects 1 in 100,000 individuals While it can lead to cirrhosis of the liver, hepatomegaly often resolves by adolescence. Other consequences can include problems with skeletal or cardiac muscle. That varies greatly, though, across affected individuals. So I believe I've addressed case 2 and case 4. They're really interesting to work on and to think through. And that is a wrap for case connections for Unit 2. I'm going to exit here.